So we've talked about a KEQ. This is a general equilibrium constant. And we've talked about a Kc. This is equilibrium constant when our units are molarity. And now we're going to talk about a equilibrium constant that is for dissolving salts. And it is called the KSP, or the solubility product constant. And we can write an expression just like we have done equilibrium constant expressions. But first of all, let's talk about dissociation. When you put an ionic solid into water, it will dissociate into its ions. And if you have enough solid in there, you will achieve a saturated solution where you have a little bit of solid on the bottom. And you will have the rate of dissolving being equal to the rate of it recrystallizing. So this is an equilibrium process between solid and aqueous. Let's look at some of these solids put into water. So we have NaCl, and we're going to put it into water. When I do this, it will split up into its ions, sodium and chlorine. You need to put the charges of the ions on them. Sodium is in the first column on the periodic table. It's an alkali metal, and it has a charge of +1. And the chlorine is a halogen. It has a charge of -1. So this is how I write it. It is correct to put the little aqueous afterwards, but I forget half the time, and I don't expect you to do it either, okay? Let's look at the next one. So we have cobalt, which is CO, and there's another chlorine. I already know chlorine's a -1, okay? Let's figure out what the cobalt is. I can see that I have 3 chlorines. Them all together will be a -3. And I just express that by having 3 negative chlorines. If all of the chlorines together is a -3, then that cobalt has to be a +3. So I will get 4 particles with this one. So the cobalt 3 chloride will split up into a cobalt ion with a charge of +3 and then 3 chloride ions. Let's look at this next one. So I have a metal with a polyatomic ion. I know that NO3 is a minus charge. You can look it up if you don't know that. And I do have 2 of them, so I'm just going to go ahead and start to balance it there. And then let's look at our nickel. So our nickel, we need to play detective. If this whole part is a -2, then we know that our nickel needs to be a +2. So I'll just put that in there. So this is how you dissociate ions from salts. So just like an equilibrium constant, if it's bigger than 1, I'll have more products. And if it's less than 1, I'll have more reactants. Our KSP tells us something. And it tells us how soluble that salt is. The larger the number, then the more soluble it is. So a large amount of the salt will dissolve. If it is really small, so you'll have a really, really negative exponent, then that means a tiny amount of the salt dissolves, and we'll say it's not very soluble. We always assume that a little bit of the salt dissolves, even if it's just 1 ionic unit splitting apart into its ions. Okay, write the solubility product constant, KSP, for the following reaction. So we write these equations just like we do any equilibrium equation. Remember, it is products over reactants. So just because this is a KSP, this is no different. I'm going to look over on my product side, and I'm going to have the concentration of my silver ion multiplied by the concentration of my bromide ion. Now let's look over on the reactant side, and notice that it is a solid. A CR is another way for saying it's a crystalline solid or a solid. Regardless, remember, you don't put solids or liquids into equilibrium constant expressions. So my KSP is done. I only have products in my KSP. That's because on the reactant side, I have a solid, and you don't put solids in equilibrium constant expressions. All right, let's look at this problem now. If the KSP is this number, what is the concentration of the silver ion to the bromine ion? Well, if I look at my silver and my bromine, notice it's a 1-to-1 ratio. So that means when my AgBr is falling apart, I end up with equal amounts of silver and bromine. So if Ag is X, then bromine is going to be X. They're going to be the same value. So that's what I'm going to plug into my equation. So again, KSP equals the concentration of the silver ion times the bromide ion. I know my KSP, 5.01 times 10 to the minus 13. And then we're going to say this is x and this is x. So I end up having x squared on this side and a number on that side. So I'm going to square root each side. And I'm going to get x equaling 7.08 times 10 to the negative 7. So this is a concentration, so I would put an M there. And remember, x is equal to the concentration of the silver ion, which is equal to the concentration of the bromide ion. So they're the same concentration. All right, let's do another one. This one's a little bit tricky in that there is some stoichiometry here. For this one, every time the copper is formed, then I get 2 of this guy formed. Let's write our KSP equation. So it's equal to the copper ion times the iodide ion squared. Let's plug in what we know. Down here at the bottom, I know what my KSP is. So 7.41 times 10 to the 8th. And then right here I have x, and here I have 2x. Now, a lot of students, they say, whoa, that looks pretty weird. 2x squared, you have to do that 2 doubly, and the answer is yes. Because you write the formula here, and now you're putting in that 1:2 ratio here into the formula. So let's go ahead and solve for x. So 2x squared is going to be 4x squared. And I'm going to multiply it by x, so that's going to be 4x cubed is equal to this number. Now, my calculator does not do cube roots very well, because that's what we're going to end up getting. So we're going to end up with x cubed is equal to this number over 4. This number is equal to 1.85 times 10 to the negative 8th. You can take that number and you can raise it to the 1/3. So if you don't have a cube root on your calculator, you can use the little caret button. And then I type in either 1/3 or I do 0.333, which is 1/3. Okay. So that's one way that you can get out of using your cube root. I end up with x is equal to 2.65 times 10 to the minus 3. Notice that in this problem, that x is what copper is. So this is my copper amount. So what is going to be this iodide? Well, it's 2x. So I'm just going to take that number and multiply by 2. And I get 5.3 times 10 to the minus 3. And these are both molarity concentrations, so an M. So salts are a little bit different when you're not given what the value of the ions are, because you have to go by that ratio. So write your formula first and then look at the ratio. In this case, we had a 1:2 ratio. It looks a little bit funny, but this is the correct way to do it.